Good morning, friends. Now we are going to discuss about the different characteristics of photoelectric effect. In last lecture, we discussed about the change in intensity, what are the effect take place on photoelectric current. Now the next characteristic is that explain the effect of potential on photoelectric effect. In photoelectric effect, the experimental arrangement is that there is the cathode or the emitter, and there is the anode. There is the collector. In photoelectric effect, we apply the potential difference between the cathode and anode, that means the emitter and collector. Now, at present, the anode is kept at the positive potential with respect to the cathode. So what's happened? Due to the incident of ultraviolet light, UV light, with the frequency F and intensity R. First, if the anode is at positive potential, therefore what are the electrons emitted from the cathode? Having the charge is negative, therefore the force of attraction is exerted on this emitted electron. Therefore, this emitted electron are attracted by the collector, and hence this electron passing to the circuit and photocurrent is formed in the circuit. So what are the effect? That means as we change the potential on collector A with respect to C. So whatever effect take place in photoelectric current, we are going to discuss. Therefore, the question is that explain the effect of the potential on photoelectric current. In photoelectric current, the collector is kept at positive potential and magnitude of potential is increased. Therefore, the photoelectric current is also increased. Now, this sentence suggests that in photoelectric current, the collector A or the anode A is kept at positive potential with respect to the cathode. Due to the positive potential on anode, what are the electrons emitted from the cathode? But there is the negative charge attacked by the collector. Therefore, all the electrons, most of the electrons are attracted towards the anode. As the magnitude of potential on anode or the collector is increases, so what's happened? More and more electrons are attracted by the collector. Therefore, most of the electrons are attracted or the moving towards or the collected by the anode. At a particular voltage on anode or the collector, all the electrons are attracted. After this voltage, as we increase the potential on anode, there is no effect on photoelectric current. So in short, as the potential on anode increases, so photoelectric current also increases because the more and more emitted photoelectron attacked by the collector. At a particular voltage on collector, the photoelectric current becomes the maximum because all the emitted electron are collected by the anode. After this voltage, as we increase the voltage on anode, now no electron is remaining. Therefore, the photoelectric current becomes the maximum, and thus the increase in photocurrent becomes zero. And this voltage is known as the saturation voltage. For that purpose here, now if the voltage on collector is increased, so photoelectric current will increase. And also, at a particular voltage, if the voltage on collector is increased, there is no increase in photoelectric current. This value of collector current is known as the saturation current. So whatever the maximum current flowing through the circuit is known as the saturation current. So maximum current flowing through the circuit. Again, as the potential on A increases, so photoelectric current is also increased because due to the more force of attraction, what are the electrons emitted by the cathode? All the electrons are attracted by the anode. Now we further increase the potential on anode. there is no increase in the photoelectric current. So the maximum photoelectric current is known as the saturation current. Now, after that, the second point is that now we are going to decrease the potential on anode. Now, the collector voltage is sequentially decreases and make negative. Now we decrease the potential on A from maximum to the 0 and then negative. So what's happened? The repulsion force act on emitted electron due to negative voltage on collector A. So what's happened? So force of attraction acting on emitted photoelectron decreases. When the potential on A becomes the negative, at that time the repulsion force starts to act on the emitted electron. Due to this repulsion force, so photoelectric current is decreases. Because what's happened? When the voltage on collector A is more negative, so repulsion force will increases for the maximum and more energetic electron only reach to the potential, reach to the anode A. When we make the anode A negative, what's happened? Repulsion force acting on electron also increases. And whatever the electron has the more kinetic energy, this electron only reaches at the anode, while the other electrons are not able to reach at the anode. Therefore, the photoelectric current is decreases and collector current decreases. The negative voltage on collector, for which the photoelectron becomes 0, is known as the cutoff or the stopping potential. It is denoted by Vc. Yes, we further going to increase the negative potential on A. For particular negative voltage, when the photoelectric current becomes 0, that means no any electron can reach at the anode or the collector. So in that case, the current flowing through the circuit will be 0. So the negative potential of anode is known as the cutoff voltage or the stopping potential. That is known as the cutoff voltage or the stopping potential. So in short, first we discuss about, as we kept the A's positive potential with respect to the C. So what's happened? Due to the force of attraction acting on emitted electron, the electron are attracted towards the collector and photoelectric current start to flow through the circuit. That means the photoelectric current is formed. Now we increase the potential on anode A. So what's happened? More and more electrons are attracted towards the collector. Therefore, photoelectric current flowing through the circuit is also increasing. For particular value of positive potential on A, the photoelectric current becomes the maximum. That means all the electrons are attracted or collected by the anode or the collector. Further, no increase in photoelectric current. So this current is known as the saturation current. This current is known as saturation current. After that, now we decreases the potential on A and makes the negative potential. So due to the negative potential on A, now repulsion force act on emitted electron. Therefore, due to this repulsion force, the photoelectric current decreases. As we increase the negative potential on A, so more repulsion force is act on emitted electron, therefore the photoelectric current is decreased. So only those electrons which have the more kinetic energy can reach to the A and forms the photoelectric current. For particular negative potential on A, the photoelectric current becomes 0. This potential is known as cutoff or the saturation voltage. And this voltage is also known as the stopping voltage, stopping potential, and that is denoted by V0. Okay. Now, on the basis of this discussion, when the photoelectric current becomes 0, the maximum kinetic energy of photoelectrons, K maximum, will be equal to the energy of electron at V0 potential, or the V0 voltage. Now listen, why at maximum negative potential on collector, the photoelectric current becomes 0. So photoelectric current becomes 0, that means the maximum kinetic energy of the photoelectrons is equal to the energy of electron at V0 voltage. Therefore, K maximum is equal to EV0 and kinetic energy is half m v square maximum. That is the kinetic energy of electron, emitted electron. So there is the important relation. Frequently we are using in numerical. K maximum is equal to EV0. Why the photoelectric current is not flowing at maximum negative potential? Because at this potential, whatever the energy of the electron is equal to the maximum kinetic energy of photoelectrons. Okay. When the frequency of the incident radiation is kept constant and the intensity of the radiation is changed for 3 stages or for 3 different values, I1 less than I2 less than I3. The graph of the photoelectric current versus stopping potential is shown in the figure. Again, we keep the frequency of the incident radiation is constant and we change the intensity of the incident light in 3 different values. I1, I2, I3. I1 is less than I2, I2 is less than I3. The graph of the photoelectric current versus stopping potential is shown in the figure. On the y-axis, we consider the photoelectric current. On x-axis, what is the potential applied on the anode we consider. For intensity I1, the frequency is constant. So stopping potential is minus V0. Now, as we increase the intensity at the same frequency, so stopping potential is also same. Further, we increase the intensity of the incident radiation by keeping the frequency constant. F is constant. So, value of the stopping potential is also same for all these intensities. So it shows that stopping potential is constant, that means the kinetic energy of the photoelectron not depends on intensity. It is the independent of intensity of incident radiation. As the frequency changes, so stopping potential is also changes. Okay? So from graph, with increase in intensity, the saturation current increases. As the intensity increases, so current flowing through the circuit is also increases. That means the saturation current, that means the maximum current, that means the maximum number of the photoelectrons is also increases. Earlier we discussed that as the intensity of incident radiation increases, so photoelectric current, that means the number of the photoelectrons emitted from the surface increases. Right? But for a given frequency, the stopping potential do not depends on intensity. So keep in mind this sentence also. Because the increase in intensity, what's happened? The saturation current increases. That means the number of the photoelectrons emitted by the emitter increases. That means the photoelectric current increases with increase in intensity. But the stopping potential is not increased. That means the stopping potential gives the measure of kinetic energy. Kinetic energy is what depends on intensity of incident light. Right? Thus, the maximum kinetic energy of the photoelectrons depends on the frequency, not depends on intensity of incident radiation. So keep in mind this. There is quite logical. From the graph, as the intensity increases, so current increases. Yeah, I1, I2, I3. But the stopping potential for all this intensity remains same, that is the V0, because the frequency is constant. Clear this? Thus, the saturation current increases with increase in intensity. But the stopping potential, that means the kinetic energy of emitted photoelectrons, not depends on the intensity, it depends only on frequency of incident radiation. Clear this? Okay. Okay, just we discussed about the effect of the intensity on photoelectric effect or on photoelectric current. We discussed that the conclusion of earlier change in intensity of incident light or the incident radiation. Only the number of the photoelectron is increases, but the kinetic energy or the energy of the photoelectron is not depends on intensity of incident light. For a given frequency, as we increase the intensity of incident light, the numbers of the photoelectron emitted by the cathode or the emitter increases, thus the photoelectric current increases. But the stopping potential is remains same. We also do the graph for three different value of intensity. So we obtain the same value of stopping potential. It means the kinetic energy or the energy of the emitted photoelectron not depends on intensity, it is only depends on frequency. Here in this question, we are going to discuss about that, explain effect of frequency of incident radiation in photoelectric effect. As we keep the intensity of the incident light constant, and we change the frequency of incident light or the incident radiation. So whatever the effect takes place in emitted photoelectrons. Right? Okay. And already we discussed the frequency of the incident radiation required the minimum value, that is the F0 is threshold frequency. If the frequency of incident radiation is increased more than the threshold frequency, whatever the effect take place in photoelectric effect, we are going to discuss this thing. Here we do the graph of photoelectric current versus the collector potential for three different values of the frequency F1, F2 and F3 of incident radiation. So here the figure shows the graph of variation of frequency of incident radiation at constant intensity in experiment of photoelectric effect. That means we keep the intensity of incident light constant and we do the graph of photoelectric current versus the collector potential for three different values of the frequency. For different frequency of incident light, for different frequency of the incident radiation, the stopping potential obtained is different, but the saturation current is same. Now, from this graph, as the frequency change or the increases, so saturation current does not change. That means the numbers of the photoelectrons emitted by the emitter is not affected by the frequency change. Or in short, as we change the frequency of the incident light at constant intensity, so the number of the photoelectrons emitted by the emitter is not affected. That means they remain constant. Right? That means the saturation current is same. For frequency F3 greater than F2 greater than F1, the stopping potential obtained also V03 greater than V02 greater than V01. That means as the given intensity of the incident radiation, the frequency is increases. So value of the stopping potential is also increases. It shows that as the frequency of incident radiation increases, so kinetic energy of the emitted photoelectron also increases, and to stop this electron or to decelerate this emitted electron, the more stopping potential is required. So from this, when the frequency of the incident radiation is more than its energy, E is equal to HF, will also move. That means as the frequency of the incident radiation is increases, so kinetic energy of emitted photoelectrons is also increases. Hence, the energy of the photoelectron emitted will depends on frequency of incident radiation. When the energy of the photoelectron is more than the most then the most stopping potential is required to stop them. So from this discussion we can say that the kinetic energy of the photoelectrons depends on the frequency of incident radiation, while the numbers of the photoelectrons emitted from the emitter depends on the intensity of incident radiation. Again we revise this. What is the effect of the frequency of the incident radiation or in photoelectric effect? Here the graph is shown the variation of the frequency of incident radiation at constant intensity versus the collector potential. From this graph, as the frequency increases, so saturation current is diminishing. That means the numbers of the photoelectron emitted by the emitter is remain constant. But the stopping potential required to stop this emitted photoelectron increases. It means the kinetic energy of photoelectrons emitted by the emitter is increases with increase in frequency of incident radiation. Clear? Okay. So here the description is that for different frequency of incident radiation, stopping potential obtained is different. But the saturation current is remain constant. For frequency F3 greater than F2 greater than F1, the stopping potential are V03 greater than V02 greater than V01. From this we can say that when the frequency of incident radiation is more than its energy, E is equal to HF, will be also more. Hence, energy of the photoelectron emitted will depend on the frequency of incident radiation. When energy of photoelectron is more, then most of the potential is required to stop them. Clear? So, only the conclusion of this discussion is that the kinetic energy, that means the stopping potential, depends on frequency of incident radiation, while the saturation current, that means the number of photoelectrons emitted, depends on the intensity of incident radiation. Okay, as we do this graph, that means the stopping potential versus frequency of incident radiation for different metal. Again, as we do the graph of stopping potential versus frequency of incident radiation for different metal. So this graph will be straight line. Now here in this graph, on y-axis we take the stopping potential, on x-axis we consider the frequency of incident radiation. So here a particular frequency of incident radiation, so here the stopping potential is start. That means as the frequency increases, stopping potential is also increases. Therefore the linear relation between stopping potential and frequency. If the frequency increases, stopping potential also increases. But the frequency is less than the threshold frequency of 0. What's happened? The photoelectric emission does not take place. Therefore, the stopping potential is not obtained. Now, from the graph, here the 2 points. For a given metal, stopping potential varies linearly with the frequency of incident radiation. So stopping potential and frequency the relation is linear. Second is, for a given minimum frequency, minimum cutoff frequency of 0, that means for threshold frequency, stopping potential is 0. If the frequency of incident radiation is this, F0 for metal A and F0 dash for metal B, the stopping potential is 0. Now the whole conclusion of this discussion is that thus the maximum kinetic energy of the photoelectrons depends on frequency of incident radiation, not on intensity of incident radiation. Again, the maximum kinetic energy of the photoelectrons depends on frequency of incident radiation, not depends on intensity of incident radiation. And when the F is less than F0, that means the frequency of incident radiation is less than the threshold frequency. For any given intensity, the photoelectric emission not take place. So in short, in photoelectric effect, the minimum frequency required is F0. If the frequency of incident radiation is less than threshold frequency at any intensity, no any photoelectrons are emitted from the emitter or the cathode. To emit the photoelectron, the minimum frequency required is F0. If F is less than F0, photoelectric emission will stop at any given intensity. So here the three sentences in photoelectric effect. For photo emission, the minimum frequency is more than the threshold frequency. Second, if the frequency increases, so kinetic energy of the photoelectron emitted by the emitter increases, and hence the stopping potential also increases. But the saturation current is not increased. And third and last sentence is that as the intensity of incident radiation increases, so number of photoelectrons increases, that means the photoelectric current increases. But the stopping potential, that means the kinetic energy of the photoelectron, not depends on intensity. Clear this? So this three sentence is the conclusion of entire photoelectric effect.